Let's take a look at exponential growth and decay and modeling data. And let's take a look at our first problem. Got A is equal to 1080 e to the 0.02 t power. And it says the exponential model describes the population of a country A in millions t years after 2006. Use this model to find the population in 2006. Well, if this starts at 2006 and we're wanting the population in 2006, you're going to put t, you're going to put 0 in for t. So this will be A is equal to 1080 e to the 0.02 times 0. Well, 0.02 times 0 is 0, so we got e to the 0 power. And anything to the 0 power is 1. So we would end up with 1080, which is just the number that's in front of the e in the first place. That's always your initial value. Let's take a look at our second problem. We got A is equal to 1080 e to the 0.02 t. It says the exponential model describes the population of a country A in millions t years after 2006. Use this model to find when the population will be 1350. So they're telling you the A amount that we're looking for. So we're going to put in 1350 for A. Equals 1080 e to the 0.02 t. Now this is an exponential equation. Anytime you have a variable in the exponent, it's an exponential equation. And if you remember our steps from before, from previous lesson, solving the exponential equation, you get the part of the variable in the exponent by itself. Well, this is the part of the variable in the exponent. It's not by itself, it's got a 1080 in front of it. So we're going to divide both sides by 1080. Like that. So 1080s cancel. And we got 1350 over 1080 is equal to e to the 0.02 t. Now after you get the power of the variable in the exponent by itself, you want to take natural log of both sides. So we'll take ln of both sides. Like that. Now, third step in solving an exponential equation says to use properties of logs to get the variable out of the exponent. Remember, if you got natural log ln, your base is e. And when those match, the log and the e's are going to cancel, and you're left with the exponent. So we got 0.02 t, and then over here the natural log. Now we're trying to solve for t, so we'll divide both sides by 0.02. So we got natural log of this divided by 0.02. And when we do that, these 0.02s will cancel. And we got t is equal to something. They wanted to, doesn't say how many decimal places, so go over to my calculator. And we'll do natural log 1350 divided by 1080. Closing parentheses divided by 0.02. Enter. And since it doesn't say what to take it to, I'll take it to, I don't know, 2 decimal places, I guess. 11.16 years. So again, you come up with a model like this, you can use it to predict what's your population going to be after a certain period of time. take a look at another problem dealing with population growth. It says, in 2000, the population of a country is 2.1 million. In 2020, the population has increased to 3.2 million. Use the exponential growth model, this, in which t is the number of years after 2000, to find the exponential growth function that models the data. So let's do that first. So we got a is equal to a naught e to the kt. Now how we're working this is a is a variable and t is a variable. Those are your only variables. So what we're trying to solve is we're trying to find out what this is, a sub naught, and we're trying to find out what the k is. Now the a sub naught is your beginning population, and then the k you can find by some data that's given. So let's read this a little closer. In 2000, and it says in which t is the number of years after 2000. So in 2000, which is the start of time for this model, the population of a country is 2.1 million. So they're telling us right away that a sub naught is 2.1. So we found one of the pieces. We just need to know what k is. It says in 2020 the population has increased to 3.2 million. Okay, so they say in 2020 our population is increased to 3.2 million. Okay, so they're giving us one example. So we're going to take this equation. We'll plug 3.2 in for a, 2.1 e, k we don't know. Now t is the number of years after 2000. So if we say 2020, that's 20 years after 2000. So t would be 20. So we got 3.2 is equal to 2.1 e to the 20k. Now this is an exponential equation. You got a variable in the exponent, so we'll go through our steps for that. First step is to get the part of the variable in the exponent, which is e to the 20k power, by itself, so we can't have any numbers in front of it. So we'll divide both sides by 2.1. So divide both sides by 2.1. And here we got e to the 20k is equal to 3.2 divided by 2.1. Now, our next step is to take natural log of both sides. So we'll take ln of both sides. Now our next step, step 3, in solving an exponential equation, is to use properties of logs to get the variable out of the exponent. Remember, if you got natural log and e, this is base e. Those e's match, so the log and the e is going to cancel, and you're just left with 20k. Always, natural log of e cancels away. So if you got ln of e, it just drops away. Now we'll divide both sides by 20. So divide both sides by 20. And this is going to give us our k. So let's go plug it in the calculator. Natural log 3.2 divided by 2.1, closing parentheses, divided by 20. And that'll give us our k. I'm going to take it out to many decimal places. So I got 021, 06, 06, 733. The rule on working problems is you never round in the middle of a problem. You round at the very end. Okay, now we know what a naught is. Remember, a naught was 2.1. That's what we set up here. And we now know what k is. So our equation, a is equal to a naught e to the kt power. A naught we said was 2.1 e k. K is all of this mess. So I got 0.0210606,733T. So that's part A. Find that model. Part B says, in which year will the population be 9 million? So for part B, they're telling us to plug 9 in for A. So that's going to be our ending population. Then we've got 2.1 e to the 0.0210606733 t power. Now the nice part about your calculator is if you have this number right here, you can press your store button and store it somewhere. Now the easiest place to store it is the X. So if I click X here and press enter, then that's now stored in X. So any place I want to do this calculation and plug in this long number, I just have to click this X button. Okay, this is an exponential equation. We've got a variable in the exponent. Well, first step is to get the part with the variable in the exponent by itself. Well, we need to divide both sides by 2.1. By itself means no numbers in front of it, no numbers after it. Now we're going to take natural log of both sides. So natural log of 9 divided by 2.1 equals natural log of e to the 0.0210606,733t. Now remember, natural log and e cancel each other out, so you're left with 0.0210606,733t. And we're solving for t, so we're going to divide both sides by that number. So we've got natural log of 9 divided by 2.1 divided by 0.0210606,733. Now let's plug this in the calculator and see what we get. So I got natural log of 9 divided by 2.1, closing parentheses, divided by this long number right here. Remember that long number, we stored it in X. So if I click X there and press enter, then that'll give it to us. Now if you have trouble with that store, just type in a long number. It's not that hard anyway. And I'll round it to 2 decimal places. I don't know how much the book will want, but 69.101. So 69.1 would be our answer. That's when the population will reach 9 million, based upon that model that we're looking at. Yeah, let's take a look at our next problem. And I guess I need to start a new page here. Okay. Then it says complete the table, and so we got country A. I think that's just a description. Here's 2007 population. Here's projected 2025 population, and that's our growth rate, our K. Well, our formula is equal to this right here, and the assumption is that we're starting our model at 2007. So this is A naught they're giving us. $143.2 E, and they're giving us K, so 0.0123 T. Okay, and what they're wanting is projected 2025 population. So they're wanting A, but T is what we have to figure out. Well, at the beginning of time is 2007. So that's our beginning for our model, the beginning time. And we want 2025. We have to figure out how many years have passed. So I'm going to take 2025 minus 2007, and that gives us 18. So T is going to equal to 18 years have passed. So to figure out what our population is, we're going to take that and we'll plug in 18 for T. You have to be careful when you plug this in. You don't want to use parentheses. Sometimes when people start putting too many parentheses in, they mess it up. So I got 143.2 second natural log, second ln for e, caret in beginning parentheses, 0.0123 times 18. And enter. So A is going to be 178 point, and I'll take it 1 decimal place, I guess. 178.7. 4 decimal places. Oh, wait a minute. No, there's 1 decimal place. Round it to 1 decimal place. Okay, so that's our answer. Let's look at number 5. Complete the table, and again, it's population growth, so we're going back to the same formula. Okay, complete the table, so we're starting 2007, 2025, and we don't know K, but we do know our initial population is 19.1. That's 2007, the beginning of time. For this model, that is. So A sub naught is 19.1. EKT. Now we need to find out what K is, and they give us the ending population and they give us the beginning population. So the ending population, 2025, is 30.8. So we put 30.8 in for A. That's still our beginning. E, K is what we're trying to find. T. Well, if we're talking about 2025 minus 2007, again, T is 18 still. So this will be 18 times K. Well, this is an exponential equation. So our first step is to get the part of the variable in the exponent by itself. So I divide both sides by 19.1. And K times 18 is 18K. Now I take natural log of both sides. And then we get natural log of 30.8 over 19.1. And remember, natural log and E cancel each other away, so that gives us 18K. So then I'll divide both sides by 18. And we've got natural log 30.8 over 19.1 divided by 18 is equal to K. Let's plug that in. So we got natural log 30.8 divided by 19.1, closing parentheses, divided by 18. Enter. And that'll be our K. Taken to 4 decimal places. So 4 decimal places, we got 0.0265. And that's all they're wanting there. They're wanting us to just find out what the K is going to be. That's our growth rate. And let's take a look at some decay models. Number 6. An artifact originally had 16 grams of carbon-14 present. The decay model A is equal to 16 E to the negative 0.123 0.000121 T. Describes the amount of carbon-14 present after T years. Now this is no different than the formula we've been looking at. We got A is equal to A naught E to the KT. So it's still the same formula. The difference is, you see how our K is negative? So that's what you'll see on these decay ones. 16 is our initial value. And see how it says it originally had 16 grams? So it starts out with that. Now, what they're asking for is how many grams of carbon-14 will be present in 10,000 years. So A is our ending amount. And 1, 2, 3, 1, 2, 1. They say will be present in 10,000 years. And it says after T years, so we're just going to plug in 10,000 for T. So I got 16. Second ln for the E. Negative 0.123121 times 10,000. Enter. And it doesn't say how many decimal places, so let me just take it to 2. So A is equal to 4.77. How many grams of carbon-14 will be present? Well, if we got decay, it starts out with 16, it's now down to 4.77. So that makes sense for the decay, doesn't it? Let's start a new page. And let's look at our next problem. Let me grab a drink too. Okay, so number 7. Remember our model. A is equal to A naught. Oops. I mean, make that big. A naught e to the kt power. It says the half-life of the radioactive element plutonium-239 is 20,000 years. Okay. So, half-life. Well, if A sub naught is our beginning life, like 20, then the half-life will be replacing A with 1/2 A naught. And they're saying is 20,000. So after 20,000 years is when you have half-life. So we want to solve for K. We want to know what a K is. So I can divide both sides by A sub naught here, because we're trying to get the part with the variable and the exponent by itself. And that's 20,000 K. Now when I divide both sides by A sub naught, those cancel and these cancel. So interestingly enough, we got 1/2 is equal to E 20,000 K. Okay, so we got the part of the variable and the exponent by itself. So now we'll take natural log of both sides. So we'll take natural log. Now remember, our third step is use properties of logs to get the variable out of the exponent, but natural log of E cancels away, and on this side we got 20,000 K. And then to solve for K, we divide both sides by 20,000. Like that. So we got natural log of 1/2 divided by 20,000. K is equal to negative 3.465 7359 e to the negative 5. What that means, that's scientific notation. That means that we have negative 3.465 7359 times 10 to the negative 5. Which means I moved my decimal place 5 places to the left. So I have negative 0.1234 3465 7359. Odds of me typing that in correctly is slim, so I'm going to store this off so I can use that. So I press my store button, and again I'll put it into, I could put it into K actually, since this is K. To get K, we do alpha, and you look for the K. Looks like the K is above the beginning parentheses. So if I push the beginning parentheses, you'll see a K on your screen, and then you press enter. Okay, so anytime I want to use that number, I'm just gonna put K on my calculation. Okay, so our formula now. Okay, so we're going to have A equals. Now it says if 20 grams of plutonium are initially present. Well, if 20 are present, that's A sub naught. E to the K, which is negative 0.1234346 57359 T. Okay, so we found our, well, they give us A sub naught. The 20 grams are initially present. We just found K by the one example they give us. And it says how many grams are present after 20,000 years. So they're wanting us to plug in 20,000 into this. We got A is equal to 20, E to the negative 0.1234346 times 20,000. Again, very nice on our calculator. Because over here, remember we stored that in K, didn't we? So I'll do 20, get the E, second ln, and that's K. So I'm going to do K, so I'll do alpha, beginning parentheses, times 20,000. And then enter. And we come up with A is equal to 10. Now they also want us to plug in after 40,000 years. So this formula right here, I'm just going to replace the T with 40,000. So I got A is equal to 20, E to the negative 0.1234346 57359 times 40,000. Now what's nice on our calculator is I can do a second enter to bring up the previous entry. And we saw that value stored in K, so I'll leave it alone. And I'm just going to change that to 4 to make it 40,000. And then press enter. And we get A is equal to 5. And then our last one, probably 60,000. So I got A is equal to 20, E to the negative 0.1234346 57359 times 60,000. Now again, if you're not very good with the calculator, just type it all in. It's not that hard. But I'm going to do a second enter because I'm lazy. And I'll go and change this to 6. And we get 2.5. And those will be our answers for that particular problem. Let me grab a drink here. And let's look at another decay model. This is number 8. So use the exponential decay model for carbon 14. A is equal to A naught E to the negative 0.123 T. Okay, so use that model. Skeletons were found at a construction site in San Francisco in 1989. The skeletons contain 20% of the original carbon 14. Estimate the age of the paintings. 20% of the original. Well, A sub naught is our original. So this right here is our original. So when we're saying 20% of the original, what we're saying is we're saying 0.20 A naught equals A naught e to the negative 0.123121 t power. So again, we're replacing a with 20% of the original. Well, I can divide both sides by a sub naught, so I'm trying to get the part of the variable in the exponent by itself. So I'll divide both sides by a sub naught. When I do that, these a sub naughts cancel there, these a sub naughts cancel here, and we get 20% is equal to e to the negative 0.1233 t. Okay, we got the part of the variable in the exponent by itself. So now we're going to take natural log of both sides, ln. So we got ln of 0.2 equals natural log of e to the negative 0.1230 t. Now, remember step 3 of solving exponential equations. Use properties of logs to get the variable out of the exponent, but natural log and e cancel each other out. So we've got natural log of 0.20 equals negative 0.000121 t. Now we're solving for t, so we're going to divide both sides by that number. So we've got natural log of 0.20 divided by negative 0.1230121 equals t. Okay, so let's plug that in, see what we get. Okay, so we got natural log of 0.2 divided by negative 0.1230121 enter. And I don't know how long, what they want us to round it to. That's probably good enough right there. Estimate the age. Okay, so it's 13,301 years old is what that says. Let me start a new page. And let's look at the next problem. It says complete the table, round half-lives to 1 decimal place, and values of k to six decimal places. This is number 9. A is equal to a naught e to the kt. Now again, we're talking about half-life, which means the a will be replaced by 1/2 a sub naught. And just like we've seen before, we can divide both sides by a sub naught, and we get 1/2 is equal to e to the kt. So let's start working with that and see what we get. Now they give us k, negative 0.052. So negative 0.052 t. The only thing that's missing is time, and I'm assuming that's what they're asking for here, is how long to get it down to the half-life. So I'm going to take natural log of both sides. So I got natural log of 1/2 equals natural log of e to the negative 0.052 t. Remember, natural log and e cancel each other out. So we got natural log of 1/2 is equal to negative 0.052 t. Divide both sides by the number in front of our t. So we got natural log of 1/2 divided by negative 0.052. And let's see what that gives us. So natural log of 1/2 divided by negative 0.052 enter. And I'll take it to 1 decimal place. So we got 13.3. And I'm gonna I'm gonna open my window here. My wife's killing me. She's got the heat on. I don't know why. I think it's like 60 degrees out or something like that. My brain will start shutting down. Now what we can do then is we could then plug this into our formula if we wanted to. Up here we got A is equal to A naught, and then okay, so K and T, and then A naught, yeah, right there. And then E to the negative 0.052 times T, which is 13.3. So we could have that model set up for us. But all they're asking for, I believe, is this right here. I'm not very good with the sciences right here, but I believe that's what they're asking for when they say half-life. Okay, let's do this one. This one wants us to find K. I'm pretty sure she's trying to kill me with that heat. Okay, let's see what they give us. I'm talking about half-life again. So, again, this is 1/2 A naught. That's how half-life always works. You can divide both sides by A naught again, and you get 1/2 is equal to E to the KT. Now they're telling us the T here. So they're giving us T is equal to 4,300. So I got 1/2 equals E to the K times 4,300. Now we can take natural log of both sides. We got natural log of 1/2 is equal to natural log of E to the 4,300K power. Natural log and E again cancel each other out, and you got 4,300K. Now divide both sides by 4,300. And let's see what we get. So natural log of 1 divided by 2, closing parentheses divided by 4,300. And 6 decimal places. So what does e to the negative 4 means is we got negative, and we move the decimal place 4 places to the left. So we got 0.12316. How many? That's 5 decimal places. 1. I guess that's 6 decimal places there, don't I? So that's K, which is what they're wanting us to find. Last half-life problem. Probably getting tired of them. A is equal to A naught E to the KT. And again, half-life. So put 1/2 A sub naught in for that. You can divide both sides by A sub naught. And we got 1/2 is equal to E to the KT. And what are they wanting us to find here? How's this any different than the last one? This is in years, and this one's in hours. And big question is, we want to leave in hours, or we want to switch it to years? I think we want to switch it to years. Doesn't really specify in our model. I'm not a real big half-life person here. Let me give you some music while I look that up real quick. I never did take chemistry. Okay, so carbon 14. Half-life is... looks like everything is in years. So let's switch it to years. It might not matter, but the book doesn't really specify. Definitely that wouldn't hurt anything, in theory. Well, it shouldn't matter since the book doesn't specify. Let's just go with it as is. So they tell us that we're trying to find K, and they say half-life is 200 hours. So put 200 in for T. Now realize our model is going to be based upon hours here, no longer years. So if whatever we might plug in, we'd have to make sure it's in hours. Take natural log of both sides. And the natural log of E cancels away, so we got ln of 1/2 is equal to 200k. Now divide both sides by 200. And let's see what our k is. Natural log of 1 divided by 2, closing parentheses, divided by 200. And k would be negative 0.03466. 466, yep. And that's our k. Now, if they did want us to switch hours to years, they don't really specify in the instructions, but if we got 200 hours, dimensional analysis, you put that over 1. If hours is up there, then hours is here. And there's 24 hours in one day. And then, since I put day up here, I had to put days down here. And ignoring leap year, we got 365 days in 1 year. So, the hours would cancel those hours, the days would cancel these days. Multiply the top part together, and we got 200 over 24 times 365, whatever that is, years. So that would be our T in years if they did want that. And I'm sure I'll get somebody posting a comment saying it's always in years. And like I say, I never took chemistry, so I'm not a big I don't have a lot of knowledge in that area. Okay, next problems are interest. So let me write down the interest formulas. And these first ones, let me take a look here. Okay. There's two types of formulas. And for interest, if it doesn't, this is the first type, if it doesn't say continuous, and that's kind of a weird way of putting it, but that really is what guides us. If it doesn't say continuous, the formula you want to use is A is equal to P times 1 plus R over N to the NT power. Now A is our ending amount. P is our principal or beginning amount. R is our rate, and that should be in decimal form. So if they give you 3%, then you would use 0.03. Remember, you move your decimal 2 places to the left to put it in decimal form. And then we got T. This would be your time in years. So if they tell you 6 months, then you would convert that to years. It'd be 1/2 or 0.5. Now our N is the number of times compounded per year. So that's the number of times compounded per year. Compounded is a fancy word saying calculated. You calculate the interest, and then you take that interest and you put it back into your account. That's what compounded means. It's builds. Now, they never give you the end directly. They give you it indirectly. They'll tell you it's compounded annually. In that case, n is equal to 1. They'll tell you it's semi-annual. N is equal to 2. They'll tell you it's quarterly. N is equal to 4. They'll tell you it's monthly. N is equal to 12. They'll tell you daily, excluding leap year. N is equal to 365. And I think I forgot weekly, didn't I? Let me put weekly in there. Weekly, N is equal to 52. And some problems may say hourly. And that's 365 times 24. Well, let's take a look at some problems dealing with this then. Given interest is being compounded monthly, principal is 2,000, time is 2 years, and rate is 3%. Finding any amount. Nowhere does it say continuous. It says compounded monthly, actually. So the formula we want to use is A is equal to P times 1 plus R over N to the NT power. And let's see what they give us. Interest is being compounded monthly. Well, that means that monthly means N is equal to 12. Principal is 2,000, so P is 2,000. Time is 2 years, so T is 2. And rate is 3%. And I want it in decimal form, so rate will be, R will be 0.03. It says find the ending amount. So they want to know what A is. Okay, so put 2,000 in for the P. 1 plus R is 0.03. Divide by N, which was 12, raised to the NT power. So we'll have 12, and I'll put a little times here. T, which is 2. Now you'll be better off to do part of this in your head. So I got 2,000 times 1 plus 0.03 over 12. 12 times 2 is 24. And let's go put this in. So I got 2,000, beginning parentheses, 1 plus 0.03 divided by 12. Closing parentheses, caret 24. And I'll round these 2 decimal places. So A would be 23.51. And let's look at our next example, number 13. Given interest is being compounded quarterly, ending amount is 5,000, time is 5 years, and rate is 4%. Find the beginning amount. Nowhere does it say compounded continuously, so it doesn't say continuously. So the formula we want to use is this one again. And let's see what they give us. Interest is being compounded quarterly. Well, compounded quarterly means N is equal to 4. Ending amount is 5,000, so they're telling us A is 5,000. Time is 5 years, so they're telling us T is 5. And rate is 4%. So R is going to be 0.04. Find the beginning amount, or the principal. So they're wanting us to find P. Okay, so let's plug in what they give us. We got 5,000 for A. P we don't know. 1 plus R, which is 0.04, divided by N, which is 4, raised to the NT power. So this would be 4 times 5. Now 1 plus 0.04 divided by 4. 4 times 5 is the 20th power. Well, 1 plus 0.04 divided by 4 raised to the 20th power. That's just a number. So to get P by itself, we're going to divide both sides by that number. So we'll divide both sides by 1 plus 0.04 divided by 4 to the 20th power. Like this. And when we do that, this is going to cancel with that. And we got P is equal to this right here. So 5,000 over 1 plus 0.04 divided by 4 to the 20th power. And let's put that in our calculator. So I got 5,000 divided by beginning parentheses 1 plus 0.04 divided by 4, closing parentheses caret 20. And we got 4,097. I'll take it 2 decimal places, 72. And that's our answer. Let me start a new page, and we'll look at the next problem. Given interest is being compounded daily, ending amount is 6,000, beginning amount was 5,500, and rate is 7.2%. Find the time. Well, nowhere does it say continuous. So we want to use this formula. And let's write down what they give us. Interest being compounded daily. That tells us N is 365. Ending amount is 6,000. So they're telling us A is 6,000. Beginning amount was 5,500. So P is 5,500. Rate is 7.2%. And I'll put that in decimal. 7.2% is 0.072. And it says find a time. Now what we're doing, in case you're wondering, is I'm going through this formula here, and I'm solving for all of the variables. I'm solving for A, for P, for R, and for T. Now we never solve for N. That never makes any sense. So let's plug in what they give us. So A is 6,000, P is 5,500, 1 plus R is 0.072, divided by N, which is 365, raised to the NT power. So 365 times T. Now this is an exponential equation. You have a variable in the exponent. So remember our steps for that. First step was to get part of the variable in the exponent by itself. So we need to divide both sides by 5,500 to get rid of that 5,500. So take 6,000 divided by 5,500 equals 1 plus 0.072 divided by 365 to the 365 T power. Second step was to take natural log of both sides. So take ln of both sides. So we got ln of 6,000 over 5,500 equals ln of 1 plus 0.072 divided by 365 to the 365 T power. Now, our third step was to use properties of logs to get the variable out of the exponent. So if you have log of something to a power, remember you can take the power and put it out in front. So we've got a natural log of 6,000 over 5,500 equals 365T natural log of 1 plus 0.072 divided by 365. Now we're solving for T. 365 is a number. Natural log of 1 plus 0.072 divided by 365 is a number. So to get to T by itself, we're going to divide both sides by those two numbers. So we've got ln of 6,000 over 5,500 divided by 365 natural log of 1 plus 0.072 over 365 equals 365T natural log of 1 plus 0.072 over 365 And again, dividing both sides by that. This is going to cancel with that, and the 365 cancels with the 365. So t is going to equal to this mess on our left side here. Now to plug that in your calculator, the top part's okay, but the bottom part, if you have more than a single number, a single variable, or a single ln, then you have to put parentheses around it. So when we plug that in, we got to put parentheses around the bottom. So we'll do natural log. This is the top part. 6,000 divided by 5,500. Closing parentheses divided by our bottom part. So I'll put a beginning parentheses on our bottom part. 365 natural log of 1 plus 0.072 divided by 365. Closing parentheses on the natural log, closing parentheses on the denominator, and enter. So t is going to equal to, I don't know, I'll take it to one decimal place. 1.2 years. Let me start a new page here. Then we'll look at the next problem. What problem was that? That's number 14. And let me grab a drink. I think the next one's a continuous. Yeah. That formula is a little bit easier. Number 15. Okay, given interest being compounded semi-annually, ending amount is 7,000, beginning amount was 5,000, time was 30 years, find the rate. Nowhere does it say continuous. So we want to use this formula here. And let's see what they give us. Interest is being compounded semi-annually. That means n is 2. Ending amount is 7,000, so A is 7,000. Beginning amount was 5,000, so P is 5,000. Time was 30 years, so T is 30. And find a rate, so we're trying to find R. Okay, so let's plug in what they give us. So we got 7,000 equals P, which is 5,000, times 1 plus R, R we don't know, over N, which is 2, raised to the NT power. So we'll have 2 times 30. Again, I'm going to do a little bit of math here. 2 times 30 is 60. Now we're trying to get R by itself. That's our goal. We can get a step closer by dividing both sides by 5,000. So we got 7,000 divided by 5,000 equals 1 plus R over 2 to the 60th power. Now here I can cancel these zeros at the end. Top and bottom both divisible by 1,000. So we got 7/5 equals 1 plus R over 2 to the 60 over 1 power. So we wrote the exponent in fraction form. If you remember the beginning of the course, if you got a something, that's really specific, I know, but you got something to a fractional power, you can get rid of the power by raising both sides to the reciprocal of that. So we're going to take both sides to the 1 over 60 power. And over here we'll do the same thing. I mean do that. There we go. So this is 60 over 1, and we're raising it to the 1 over 60 power. Now when you do that, these 60s will cancel. Of course, the 1's trivial. They go away anyway. And we got this. So we're going to have 7/5. Oh, by the way, back in earlier material, we said that if this is an even power, so if that's even, we put a plus or minus on the other side. We didn't put a plus or minus here. Now, I didn't forget it. It's not a screw-up. Just think what we're finding. We're finding R. You can't have a negative. Your rate can't be negative. That wouldn't be good. So that's why I didn't worry about the negative. Well, I'll take the 1 over. So we get negative 1 plus 7/5 to the 1/60th power equals R over 2. And then we'll multiply both sides by 2. So we got 2 times negative 1 plus 7/5 to the 1/60th power equals R. Now this is a little tricky to enter. Pretty much you just enter it as you see it, but if you ever have more than a single number or a single variable in your exponent, you have to put parentheses around it. So this 1 over 60, I'd put parentheses around it. So let's type that in now, see what we get. So again, I'm going to type it in pretty much exactly as I see it. So I got 2, beginning parentheses, negative 1, plus, beginning parentheses, 7 divided by 5, closing parentheses, caret, and then beginning parentheses, 1 divided by 60, closing parentheses on the this very beginning one, and enter. So R is equal to 0.011247. I'm not sure how many decimal places. Now this is in decimal form. Rate should always be put back into percent form. So we want to move our decimal 2 places to the right, and we'll get 1. I'll take it 2 decimal places. 1.12%. And that's our answer. Now let me start a new page since we're going to the next type. Now you're finding interest again, but this time they now say continuous. So it says continuous. This is the PERT formula. So we got A is equal to P times E to the RT power. Now A is our ending amount still. That hasn't changed. Our P is our beginning amount, or our principal. R is our rate, and that has to be in decimal again. So if we had 3%, for example, we'd use 0.03. And T is our time, and again, that's in years. So let's look at this problem. It says given interest is being compounded continuously. Again, it says the word continuous. That's why we want to use PERT formula. Let's see what they give us. Principal is 2,000. So principal is 2,000. Time is 2. So T is 2. Rate is 3%. R is equal to 0.03. It says find the ending amount. So we're trying to find A, the ending amount. Well, let's plug in what they give us. P is 2,000. E to the R, which was 0.03. I'll do a little times here. T, which was 2. You have to be careful when you plug these into the calculator. A lot of people screw these up. We're going to do 2,000. E, so we do second, ln, and 0.03. Do not put any extra parentheses in here. Just do it times, and then 2, and then enter. So we'll get 2123.67. And that's our ending amount. Let's look at our next one. Say given interest is being compounded continuously, so it says continuous. So we're going to use our PERT formula. See what they give us. Compounded continuously, ending amount is 5,000. So A is 5,000. Time is 5 years, so T is 5. Rate is 4%, so 0.04. It says find the beginning amount. So they're asking us what is P. And grab a drink. Okay, so A, we put 5,000 in for A. P we don't know. E, R was 0.04 times T, which is 5. Now E to the 0.04 times 5, I don't know what it is, but it's just a number. So to get to P by itself, we're going to divide both sides by that number. So we'll divide both sides by E to the 0.04 times 5 power. Now if you want, plug this in your calculator and get the decimal, and then divide both sides by the decimal. As long as you take it out all the decimal places your calculator says, you should be fine. So I'm going to put in 5,000. Just don't round is what I'm saying. Divide by second ln for the E. And then we got 0.04 times 5. Enter. So our P is going to equal to 4,093.65. And let me shift position in my chair here. Sitting too long. Let's look at our next problem. Given interest is being compounded continuously. Again, this is a PERT formula. And let's see what they give us. Ending amount is 6,000. So A is 6,000. Beginning amount is 5,500. So P is 5,500. And rate is 7.2%. So R is 0.072. Want to change it to decimal. Find a time. So we want to know what T is. Okay, so we got 6,000 for A, 5,500 for P, E to the R, which is 0.072, T. Now this is an exponential equation. We got a variable in the exponent. So we want to get the part of the variable in the exponent by itself. So we'll divide both sides by 5,500. So we got 6,000 divided by 5,500 equals E to the 0.072 T. Our next step is to take natural log of both sides. So we've got natural log ln of 6,000 over 5,500 equals ln of E to the 0.072 T. So we got natural log of 6,000 over 5,500. Remember, natural log and E cancel each other out. So we got 0.072 T. And then we'll divide both sides by 0.072. So we got natural log of 6,000 over 5,500 divided by 0.072. And let's see what that gives us. So we got natural log of 6,000 divided by 5,500, closing parentheses, divided by 0.072. Enter. And we get, I don't know, one decimal place, 1.2 years. Like that. And let me start a new page here. Let's look at our next problem. Given interest is being compounded continuously, so again it's our PERT formula. Ending amount is 7,000, so they're telling us A is 7,000. Beginning amount was 5,000, so P is 5,000. Time was 30 years, so T is 30. They say find R, find the rate. Okay, so let's plug in what we got. 7,000 for A, 5,000 in for P, E to R we're trying to find, and T we know, T is 30. So this becomes 30R. Well, divide both sides by 5,000. Take natural log of both sides. Hopefully this is becoming torturous. Hopefully this is becoming second nature now. So then we got natural log of 7,000 over 5,000. Natural log of e cancels away, and we got 30r. And then we'll divide both sides by 30. I know word problems aren't the most exciting thing. And so then we get r is equal to that. So we got natural log of 7,000 divided by 5,000, close parentheses, divided by 30. Enter. And so we got r is equal to 0.0112. Now we want to convert that to percent, so we'll move it 2 places to the right, and we got 1.12% for our r. Last problem. Says given interest is being compounded continuously, so guys still got that same formula. Beginning amount was 2,000, so P is 2,000, and rate is 4.1%, so R is equal to 0.041. Find out how long it will take the money to double. How long? That's T. Money to double. Well, if we start with 2,000, doubling it means we'll end up with 4,000. So I'll put 4,000 in for the A, 2,000 in for the P, e to the r, which is 0.041 t. Now again, we want to get the part of the variable and the exponent by itself, so I'm going to divide both sides by 2,000. And get that. Now 4,000 divided by 2,000 is 2, just to simplify it a little bit. Take natural log of both sides. This is how you solve an exponential equation. And we get natural log of 2. Natural log of e cancels away, and you got 0.041 t. And then we want to divide both sides by 0.041 to get the t by itself. And let's see what we get. Natural log of 2, close parentheses, divided by 0.041. Enter, and we get t is equal to 16.9. Now what I find interesting about this formula is when you're finding how long it'll take to double, the amount you put in, your beginning amount, has nothing to do with how long it takes, because it'll always cancel away and you'll always be left with a 2 on the left side. So it's interesting, at least for somebody that likes math. And that's the end of that section, so let me end the recorder.